Hello everyone. Today we are going to solve the problem of free fall of an object under the influence of gravity and aerodynamic drag force. Although at first sight this problem might look simple, it is actually very important for a number of practical engineering problems. In particular, in this tutorial, we explain how to derive the dynamics of this system and how to analytically compute the expression for the velocity of a free-falling object. Also, in this lecture, you will learn that after some transient time, the velocity reaches a constant value. That is, the gravity and drag force become equal, which produces zero acceleration. That is, it produces constant velocity. Here's the problem formulation. A ball with a mass of m freely falls from the initial height of y0. The initial velocity of the ball is 0. The intensity of the aerodynamic drag force acting on the ball is given over here. It's proportional to v squared, where v is the current velocity of the ball and k is a constant. We assume that the buoyancy force can be neglected. Then, we want to determine, first of all, the velocity of the ball before it reaches the ground. Then, the velocity of the ball at the moment it hits the ground. Then we want to determine the steady-state velocity of the ball, where we assume that the steady-state velocity is reached before the ball reaches the ground. Okay, let's solve this problem. The first step is to construct a free body diagram of this system. The free body diagram is given over here. mg is the gravity force and Fd is the aerodynamic drag force. The next step is to derive the dynamics of this system. We start from the Newton's second law. We can write mass of the ball times the acceleration of the ball is equal to the sum of all the forces acting on the ball. Over here, we assume that the ball is actually modeled as a point mass. Consequently, we neglect the volume of the ball and we just consider a ball as a single point. From Newton's second law, we have mass times acceleration is equal to sum of all the forces acting on the material point. That is, it's equal to mass times gravitational acceleration constant as a vector plus Fd, where Fd is the aerodynamic drag force. Next, we introduce the unit vector of the y-axis, denoted by j, and we will scalarly multiply this equation by this unit vector. That is, we will compute the projection of this equation onto the y-axis. We have m times a, where a is the intensity of the acceleration, is equal to, let's see from here, the projection of mg onto the y-axis is minus mg, and the projection of this force Fd is simply plus Fd. Taking into account the expression for Fd, we can write this equation like this: k multiplying velocity squared. Next, we can write the acceleration as a is equal to first derivative of velocity with respect to time. By substituting this expression in this equation, we obtain m dv over dt is equal to minus mg plus k v squared. In order to compute the velocity, we need to integrate this equation. That is, from this equation, we need to compute the expression for velocity v. So how to do that? To integrate this equation, we will use the following trick. We can transform the left-hand side of this equation like this: mass multiplying, and over here I will introduce dy. Then Since I have dy, I also have to have here dv over dt, so I need to add few terms. Over here, I will take this dt and I will divide dy by dt. Then I'm left over here with dv, and I need to divide dv by dy such that these dy over here and this dy over here can be cancelled, and I will have the left hand side over here. That is, to summarize, this left hand side over here is equal to this left hand side. The right hand side stays the same. Here, you need to observe that the first derivative of position y with respect to time is actually the velocity. Consequently, we have dy over dt is simply the velocity. Okay, let's substitute velocity in this equation. Consequently, we obtain mass times velocity multiplying derivative velocity with respect to the height y is equal to minus mg plus kv squared. Okay, now we will move this term over here to the left side, and dy we will move to the right side. Consequently, we have m multiplying v times dv over kv squared minus mg is equal to dy. Some of you might recognize over here that if we integrate this expression on the left hand side, we will actually obtain an ln function, and that's true. Now, let's do a few transformations. Since I want to use an ln function, I need to make sure that this expression in the denominator is positive. Now it's actually negative. This is because kv squared minus mg is negative, that is, mg is larger than kv squared before the ball reaches a terminal velocity. Consequently, instead of using kv squared minus mg, I will simply write this. I will take the minus out. In the denominator, I will have mg minus kv squared. In the numerator, I will have m multiplying v dv is equal to dy. Okay, we need to integrate both the left-hand side and the right-hand side of this equation. Let's start with the left-hand side. We need to compute this integral. I will take the minus over here, and we have mv dv over mg minus kv squared. Over here, we will use the substitution. What is the substitution over here? I will introduce a new variable called s, and I will say that s is equal to mg minus kv squared. What is ds? ds is derivative of mg is 0, consequently I will have 0 over here, and if I differentiate kv squared, I will obtain minus 2k v dv. Aha, okay, let's see what is v dv. From this expression, v dv is actually equal to minus ds, and over here I have over 2k. Next, we need to substitute s and v dv. Let's do that. We have integral minus, let's see what do we have here. In the denominator, obviously we will have s, probably some other constant, we will see later. What do we have in the numerator? Instead of v dv, we write minus ds over 2k. This minus goes out, and if we multiply minus and minus, we obtain plus over here. Then, what else do we have? We have m Then we have ds, and over here we will have 2k. Let's continue. M over 2k is a constant, and we can write it outside of our integral, and we need to integrate ds over s. Since s is positive over here, we have ln function of s. And notice over here that I don't need to write an absolute value. And another thing, we will have a constant over here. However, I will not write a constant since I will substitute back as by this term over here, and then I will substitute the initial condition in the original expression. Over here, for clarity, I repeated the last two equations. We started from this equation, then we integrated the left-hand side, and we obtained this equation. If I now substitute s over here, I will have m over 2k ln of s, and s is mg minus kv squared. Okay, good. Now, let's integrate the complete equation. I will write it over here, minus integral mv dv over mg minus kv squared is equal to the integral of dy. Over here, we need to substitute the bounds. So what are the integration bounds? We integrate dv term over here, starting from initial velocity that's equal to 0 to some final velocity. Let's denote it like this, v final. Similarly, let me just nicely denote here, vf. Similarly, we integrate dy term from y0, this is the initial height, until some final height, yf. Okay, now we have over here that this integral is equal to this term over here. Consequently, we can write m over 2k ln of mg minus kv squared, and then we have the bounds. The bounds are 0 until v final, and this is equal to integral of dy, simply y, from y0 until y final. To illustrate over here, here's our ball, and y is always measured from here. Over here we have some initial position, and over here we have the final position. This is y final, and this is y initial. Denoted by y0. The velocity v is over here, and the final velocity is over here, v final. Let us now substitute these bounds. First, let's substitute the left-hand side. On the left-hand side, we have the following: m over 2k multiplying, let's see, ln of mg minus k v final squared minus, over here, ln 0 for velocity will produce ln of mg. And this is equal to y final minus y0. Now, we can transform this expression like this. By using the basic rules for manipulating with log functions, we can write this difference of log functions as division of an arguments. Consequently, we have mass over 2k multiplying ln mg minus k vf squared over mg. then close is equal to y final minus y0. Over here I use this rule. Namely, it's very well known that if you have ln x over y, this is actually equal to ln x minus ln y. And that's precisely what I used over here, where y is mg and x is mg minus kvf squared. Next, from this expression, we need to compute vf. Let's do that. First of all, from this equation, we have that ln of mg minus k vf squared divided by mg is equal to, let's see what do we have over here, 2k over m multiplying y final minus y0. Okay, then from this equation we have that mg minus k vf squared over mg is equal to e to the power 2k over m yf minus y0. Next, let's analyze this expression over here, and let's see what we have. We can write this term as 1 minus k over mg multiplying vf squared, and the right-hand side stays the same. Let's write it down. 2k over m yf minus y0. From this expression, we have that vf squared is actually equal to. Now, e goes on this side, and this term goes on this side, and we divide the result on the left-hand side by mg over k. Consequently, vf squared is mg over k multiplying 1 minus this guy over here, e to the power 2k over m. Let me write nicely m over here, yf minus y0. And from this equation we have that vf is a square root of mg over k multiplying 1 minus e to the power 2k over m multiplying yf minus y0. And that's the final expression for the velocity vf. Here again is our solution. This is the velocity of the ball at some time instant t corresponding to the height yf. Graphically, if this is the ground, this is our ball. Over here is the height yf in this equation, and here's the velocity vf. However, we need to determine the velocity at the moment the ball hits the ground. That is, we need to determine the velocity just before this point over here. How to do that? Well, to do that, we obviously need to substitute yf for the corresponding value. At the moment the ball hits the ground, yf becomes 0. And let's see the expression. Then vf is equal to v ground is equal to square root of mg over k multiplying 1 minus e to the power 2k over m, and let's see what do we have over here. Yf is equal to 0, and consequently we will have minus y0. And this is the final expression for the velocity just before the ball hits the ground. And don't forget to close this parenthesis over here. Next, we need to determine the steady state or the terminal velocity. So what is a terminal velocity? Let us analyze this scenario. Let us assume that the initial height y0 is relatively large. This is actually y0, the distance from here until the ground. If y0 is very large, then let's analyze the dynamics of this system. If we let the ball falling, what will happen? Will the ball constantly accelerate or not? Well, the second Newton's law that look like this, minus mg plus kv squared, will produce the answer. Let's see what happens. What happens initially? Initially, since the initial velocity of the ball is 0, this term over here will be equal to 0. That is, at the initial point, we will have ma is equal to minus mg. And the ball will accelerate only due to the gravitational acceleration. Then, after some time, for example, at this height over here, we'll have that the acceleration will be minus mg plus kv squared. And that's precisely this term over here. So what will happen with the acceleration? The acceleration that will be obtained by dividing minus mg plus kv squared over m will actually decrease. Why is that? Because the velocity vector will actually increase. And then what will happen? Due to this term over here, the acceleration will actually decrease. And if you let the ball falling for sufficient amount of time, we will see that basically kv squared term becomes approximately equal to minus mg, which means the acceleration becomes approximately equal to 0. This means that after some height, for example, over here, the acceleration will become 0, and after this moment, the ball will fall with a constant velocity, and let's call this velocity Vs, where Ss is the steady state. Again, the physics of this problem tells us that if you let the ball will accelerate until certain height over here, after which the ball will move with a constant velocity. Where is this height in this moment? Well, we can simply say that ma is equal to 0. This is because a is equal to 0. And we are searching for that point, and we have minus mg plus kv squared. And over here, instead of v, we will have ss. Consequently, from this equation, we have kvss is equal to mg. Don't forget the square over here. And consequently, we will have vss squared is equal to mg over k, or vss is square root of mg over k. And this is the final equation that solves our problem.